Hey guys, in this video, we are going to focus on finding compound probabilities and differentiating between independent and dependent events. So let's dive into just the vocabulary and the formulas that you're going to need. Independent events, when the outcome of one event does not affect the outcome of another. Whereas a dependent event is when the outcome does affect it, is dependent on something else happening. So we have our two different formulas. So we have our probability of A and B for both. But for an independent event, you take the probability of A happening times the probability of B happening. For dependent, you have the probability of A happening times the probability that B after A occurs. So the probability of event B happening is depending on what happened the first time. So let's look at some examples. So let's look at some independent events first. So we have a dice is rolled 3 times. What is the probability of getting ones on each roll? If you know anything about a die, if you roll a die once, you get a number. If you pick it up and roll it again, you get a number. That roll of the second die is not affected by the roll of the first die. That is what makes this an independent event. So dice have numbers 1 through 6 on them. So there are 6 possible events. On a die, there are numbers 1, 2, 3, 4, 5, and 6. So there's a 1 out of 6 chance of rolling a 1 on the first roll. There's a 1 out of 6 chance of rolling on the second, times a 1 out of 6 chance of rolling on the third. So the probability of rolling a 1 times the probability of rolling a 1 times the probability of rolling a 1 on the third roll. So remember, with fraction multiplication, we multiply numerator times numerator and denominator times denominator. So 1 times 1 times 1 is 1 on top. 6 times 6 times 6 would be 216. This fraction does not simplify, so that would be your answer. And as a reminder, you can write that as a decimal or as a percent. Let's look at example B. A coin is tossed. So again, a coin toss, the first toss is not going to affect the second toss. So that is why it's an independent event. So a coin is tossed, then a day of the week is selected. What is the probability of getting tails and then a day starting with the letter that ends in T, or starts with T rather? So again, these events are not related. They are not dependent on one another. The rolling of a die is not going to affect the day of the week. So we have a coin is tossed. We want to get tails. There's one tail out of 2 possible options, right? I could have a heads or a tail. Times days that start with T are Tuesday and Thursday. So we have 2 out of 7 days in the week. Simplify your fractions if you can. Notice I have a 2 on top, 2 on bottom, so I actually can cancel those 2's out. So I'm left with 1 on top, 7 on the bottom. Perfect. Let's look at some more. So we have a bag contains 8 red crayons, 14 purple crayons, 6 yellow crayons. I'm actually going to use orange because yellow doesn't show up very well. And then 4 green crayons. A crayon is selected, replaced. This is a key word. We'll notice that in our next example, but that word replaced is very important. So a crayon is selected, replaced, and then another is selected. Find the probability. So let's go ahead and let's find the total number of crayons. So I'm going to have the 8 red crayons plus the 14 purple crayons plus the 6 yellow crayons plus the 4 green crayons. Add all of those up, and I have a total of 32 crayons. So in this first example, we're looking for the probability of drawing a purple and then a yellow. So the probability of drawing a purple, I have 14 purple crayons out of 32 total crayons, times the probability of then drawing a yellow, I have 6 yellow out of 32 total crayons. And then before you go to the next step and multiply straight across, because these numbers would be very large, it's actually easier to simplify now and then multiply. So 14/32, both the numerator and the denominator are divisible by 2. So I'm going to simplify that down to 7/16. And then 6/32, both the numerator and the denominator are divisible by 2. So that simplifies down to 3/16. So again, slightly smaller numbers. And then what this means is you will not have to simplify in the end because nothing simplifies any further. So now I go ahead, I multiply numerator times numerator, denominator times denominator, and I get 21 over 256. Or as a decimal, that would be approximately 0.0820. Or as a percentage, take that decimal, move it 2 to the right to get 8.20%. Let's look at the probability of a green and then red. I have 4 out of 32 green times red. I have 8 red out of 32 total crayons. Simplify your fractions ahead of time. Again, this will save you work in the long run. So that first fraction simplifies down to 1/8. That second fraction, both denominator and numerator are divisible by 8. So that second fraction simplifies to 1/4. So now I can multiply straight across to get 1 out of 32. And again, that's not going to simplify further because I simplified at the beginning. And then approximately 0.0313 or 3.13%. Let's look at the probability of getting 2 purples. So again, this is where the not replacement part is especially important. I have 14 purple crayons out of 32. I draw it and put it back, so I still have 14 out of 32 possible purple crayons. So simplify the fractions. So I end up with 7/16 times 7/16. Multiply straight across, so numerator times numerator, denominator times denominator to get 49 out of 256, which ends up being fairly likely. We end up with 0.1914 or 19.14%. All right, last one, 2 yellows. So I have 6 yellow out of 32 crayons. I draw it, I put it back, so I still have 6 out of 32 yellow crayons. And then again, simplify before you multiply. So I'm going to go ahead and simplify that down to get 7/16. Whoops, sorry. I was looking at the wrong line. I was looking at the line above. That should be 3/16 times 3/16, which would give us 9 out of 256. Which this is a little less likely, obviously, than drawing 2 purples. This would be approximately 0.0352 or 3.52%. All right, perfect. Now let's talk about dependent. So I actually have the same problem. There's a subtle difference. So I have 8 red crayons. I have the 14 purple crayons. I have the 6 yellow. I have the 4 green crayons. A crayon is selected and not replaced. That makes this a drastically different problem. So now the second draw is going to depend on what happens in the first draw. So that's what makes this now a dependent event. So the probability of drawing a purple and then a yellow. So I have 14 purple out of the same 32 crayons. But now I'm not putting it back. So when I do my second draw, I still have 6 yellow crayons in this bag, but now I only have 31 crayons left because I took one of those crayons out for the purple draw. So again, like the previous slide, simplify what you can. So we end up with 7/16 times 6/31. And again, you can multiply straight across, but then you're going to be dealing with larger numbers. So I try to look again to see if there's anything else I can simplify further. I noticed that both the 16 on the bottom and the 6 on top, because remember, this is just going to form one big fraction where you take 7 times 6 and 16 times 31. So I noticed that the 6 and 16 are both divisible by 2. So I'm actually going to simplify a little bit further to end up with 7/8 times 3/31. So now I'm at a point where when I multiply straight across here, and I end up with 21 over 248, this is not going to simplify any further. The only numbers that go into 21 are 7 and 3, and 7 and 3 does not go into 248. So that would be the probability then of drawing a purple and then a yellow without replacement. So this would be approximately 0.0847 or 8.47%. And then we can go ahead and do the probability of a green and then red. So green is going to be 4 out of 32. And then the red, there are still going to be 8 red crayons, but now there's only 31 crayons in the bag. Simplify those fractions if you can. So 8/32 actually simplifies down to 1/8. And then times 8/31. But then you'll notice you have an 8 on top, 8 on bottom. So you can actually take and cancel out those 8s, and you're left with 1 out of 31. And then that would be, as a decimal, approximately 0.0323 or 3.23%. And then we can do the same thing with our probability of 2 purples, but it's going to be a little bit different. So you have 14 purples to start with out of 32. But if you draw one of the purples, now you're only left with 13 purple crayons out of 31. So simplify what you can. So that 14/32 actually becomes 7/16 times 13 out of 31. This isn't going to simplify any further. 13 is prime and 7 is prime, and neither of those numbers go into 16 or 31. So we multiply straight across, and we end up with 91 out of 496, which is approximately 0.1835 or 18.35%. All right, last one, the probability of 2 yellows. You start off, you have 6 out of 32 crayons that are yellow. After you draw 1 yellow crayon, you'd only have 5 yellow crayons left out of 31 crayons left in the bag. Simplify what you can, so we end up with 3/16 times 5/31. Can't simplify any further because 5 or 3 does not go into 16 or 31, so multiply straight across. Then we get 15 out of 496 for our probability. But as a decimal, that would be 0.0302 or 3.02%. All right, awesome. Let's just try one more, even though I have 2 more examples on this next slide. We have a card is drawn from a standard deck, not replaced, so that tells you that it's going to be a dependent event. And then another card is drawn. What is the probability of choosing a heart and then a spade? So recall that if we talk about our hearts, there are 13 hearts out of 52 total cards. Times, there are 13 spades, so 13 and 13 of each suit. There are 13 spades in the deck, but now there's only 51 cards left. Simplify your fractions if you can. So the first fraction actually simplifies down to 1/4 times 13 out of 51, which is not going to simplify any further. So we multiply numerator times numerator, denominator times denominator to get 13 out of 204. Or again, you can write it as a decimal, or moving the decimal place 2 to the right, you would have 6.37%. Awesome, guys. And even though I have the next example, I'm just going to call it there. You just have to keep in mind that whether it's dependent or independent has to do with whether or not something is replaced. So for example, in this one, as you read through it, you find out that Steve eats the candy and then picks another one. And so that means his next choice is reduced or changed because of the event of the first. All right, guys, until next time.